Okay, thank you. Here I am again, ready to talk a little bit about the geology of the moon. First slide, please. I want to review a little bit what I covered before. Now, a few of these first couple slides that you've seen previously in the first talk, the introduction to the moon, but I wanted to just basically review a little bit to make sure that we're all on the same page. Let's remember that we're talking about the moon, which is a rocky terrestrial planet. It has a crust, a mantle, and a core. In a nutshell, it has a very heavily cratered surface. The highlands are very heavily cratered. The maria are also cratered, but a little less heavily cratered. And the reason is that they're slightly younger. So the highlands of the moon date from around 4 billion years or so. The maria flooded the moon thereafter for about 100 million years to about 3 billion years ago. And since then, we've only had the occasional impact that forms large craters like Tycho and Copernicus, and then the constant rain of micrometeorite bombardment that grinds up the rocks into a surface powder. And that material is called the regolith. Next slide. All right, just to remind you again that the near side and the far side of the moon are very different. The near side of the moon actually has quite a bit of dark, smooth material, the maria, whereas the far side is almost completely highlands, rugged, very heavily cratered, and very high in albedo. We're not quite sure why this dichotomy exists. There are a few ideas. One of the ideas is that the crust is thicker on the far side, and therefore lavas that are generated deep in the mantle of the moon have a longer way to travel to get to the surface on the far side. So therefore it's easier for them to break through and erupt on the near side than on the far side. But the fundamental reason for the dichotomy is unknown. That is a scientific question we want to answer as part of going back to the moon. Next slide. Again, the topography of the moon is quite astonishingly, has a very large dynamic range. Over 15 kilometers of dynamic range in topography from the lowest spots to the highest spots. And that's about the same as the Earth. Basically, from the bottom of the Marianas Trench to the top of the Himalayas is about 15 kilometers. On the moon, though, the cause of this topographic range is very, very different. The moon's crust is rigid and ancient. And fundamentally, all the different topographic varieties we see on the moon are caused by large impact features. And I'm going to spend quite a bit of time on that today because impact really is the fundamental process on the moon. It made most of the crustal rocks. It modifies the surface today, and in fact, going to the moon and understanding the impact process, in my opinion, is the principal scientific product of Apollo. It gave us a totally different appreciation for how planets form and evolve, and also how evolution works. Physiographically, you have the rugged uplands, the highlands, also called the terra in Latin, and the dark, smooth lowlands, the maria in Latin. Interestingly enough, in terms of general blockiness, the younger smooth maria typically are more blocky than the highlands. The reason is, the maria being younger, the bedrock is much closer to the surface. So a given size impact can dig down beneath the regolith, through the regolith layer, and excavate rock, fresh rock, and bring it to the surface. In the highlands, the regolith is so thick, it takes a very, very big crater to dig down far enough to bring up significant amounts of rocks. Next slide. Now, by physiography, effectively we mean the study of landforms and the provinces of landforms. This has actually been studied for a long time. The little image here I have at the top is from a map done in 1961 by Hackman and Mason. It was called An Engineer's Special Study of the Moon. And that was actually the first geologic mapping of the moon ever done. It was done by two geologists from the military geology branch of the U.S. Geological Survey. They had done terrain studies for the military, and they were actually assigned this by the Air Force to look at the physiography of the moon. They produced a map that's actually quite good. They recognized that the Marian highlands probably had a rock type difference. They recognized that the Maria were low, the highlands were high. They attempted to map structure when they saw it, and we'll talk about structures later. And they also they were grasping at the idea of relative age by recognizing that the highlands, the brown here, were the oldest, the yellow, maria, were the next, and then finally things that were green on top of that were craters that post-dated both of them. Again, for the first time, we saw the far side of the moon in the space age. And the image here in the middle is the Lunar 3 image of the moon taken in 1959. Which is one of the very first pictures of the moon taken from a spacecraft, and it shows a large part of the far side. The dark areas here at about 7 and 8 o'clock are part of the eastern near side. The rest of the image is on the far side of the moon. And it was quite stunning to see that the maria didn't really continue around on the far side. People were immediately struck by that, and we've been trying to explain it ever since. And fundamentally, what we saw from these data were that the moon's surface was shaped primarily by impact and volcanism. Now, originally, in the 50s, a lot of astronomers liked the volcanic explanation for the origin of craters because they were familiar with big terrestrial calderas like Kilauea in Hawaii. But the simple fact is, impact was shown to be the dominant process actually before we ever went to the moon, largely through the documented study of terrestrial impact craters, which were not fully understood mechanically until the space age. Next slide. Again, craters dominate all landforms. They range in size from micrometers to megameters. So effectively from things that are much too small to see, caused by the impact of little dust motes at cosmic speeds, all the way up to giant basins that effectively subtend almost the diameter of the planet. There is progression and change in morphology, both with age and size, and we'll talk about that in some detail. The maria are smooth, flat plains because they're replaced by fluid lavas that run out and fill the depressions, with a few minor landforms. So we see some domes and cones, we see faults, and a few miscellaneous features, and I hope to cover all of those over the course of this talk. Next slide. Just to remind you of the diversity of the landscape on the moon, the mare tend to be relatively flat except for large craters that interrupt the monotony of the smooth plains. One thing that you should keep in mind is the moon is a very small object. It has a radius of 1738 kilometers. And a 2-meter tall observer on a flat mare plain, the horizon is only about 2.5 kilometers away. So the horizon is very close on the moon. On Earth, that same horizon would be well over 12 kilometers away. So I remember right after Apollo 11, Buzz Aldrin made a comment to the effect that he was actually conscious of standing on a curved body. And I always thought that was a very strange remark. But at the same time, if you were to wander off across the mare and within a very short period of time, you would actually lose sight of the place you started from. It would be below the horizon because the curvature is very abrupt. You wouldn't have any trouble finding your way back because you could just follow your footprints. Next slide. Again, reviewing what we know about the lunar terrains. The mare tend to be actually flat to gently rolling. There can be relief up to 100 meters on them. There are craters, large craters that are greater than around 20 kilometers and less, but they're not abundant. They don't pepper the surface. They don't saturate the surface like they do in the highlands. Again, it's blockier because the bedrock's closer to the surface, and the mean slopes are on the order of 4 to 5 degrees. The highlands, on the other hand, are very rugged. They look very rough on a macro scale, at telescopic scales like this right here. This is a picture of the Apollo 16 landing site. It looks very rough, very rugged. But on a meter to decameter scale, it's not that rough. It's smooth and rolling. And the Apollo 16 site here at the Cayley Plains actually had a lot of relatively flat area. The astronauts had no trouble traversing it either by foot or by rover. Next slide. Okay, now I want to talk about the cratering process, because this is the fundamental process that shaped the moon and, in fact, shaped all the terrestrial planets. This diagram here is from a book that you can actually get online, and I have the reference at the end of my talk, and you can look it up, and I urge you to do so. It's by a guy named Bevan French, who is one of the masters of study of shock metamorphism, and he wrote a book for the Lunar and Planetary Institute called Traces of Catastrophe, where he describes how you recognize shock metamorphism, and he describes the cratering process in some detail in that book. But fundamentally, objects hit the moon at cosmic speeds. The mean impact speed of debris hitting the moon is about 20 kilometers per second. So that means that basically half the material hits at speeds higher than that, the other half hits at speeds lower than that. Remember, lunar escape velocity is only about 2.2 kilometers per second. So things that hit the moon at high speeds are going to eject material off the moon at greater than escape velocities, at least initially. And that, in fact, is the source of lunar meteorites. That's why we have rocks on the moon that have actually been blasted off the surface of the moon. They've entered the circumterrestrial orbital sphere and eventually been captured by the Earth and landed as meteorites. The top view shows the penetration, the contact and penetration, and at that point, these objects are moving so fast that effectively they have more kinetic energy in them than is required to vaporize them for any reasonable geologic material, whether they're stony meteorites or whether they're solid irons. So effectively, all the material that hits the moon becomes vaporized. It hits at such speeds that there's so much energy, not much really survives. Now, it's possible that some parts of that debris, as it hits the moon, it'll send a shock wave through the body. You might actually spall off material off the back side of the projectile, especially if the projectile is over a few hundred meters in size. That spalled off material will be spalled off at speeds approximately the same as the impact speed. So what is the net speed of that spall material to the surface of the moon? Well, it's 0, because if you're hitting at 20 kilometers and I spall off pieces at 20 kilometers in the opposite direction, then effectively I have a 0 speed relative to the moon. So it is possible, and in fact we should look for meteoritic debris in the lunar regolith, and we have found very small chunks of that in the Apollo sample collections, but in terms of mass, it's a very small fraction of the total mass hitting the moon. Now this collision actually acts like a point release of energy. As this material hits the moon, it penetrates on the order of its diameter. So if I have a 1 kilometer object, it'll penetrate down about a kilometer. And as it's vaporized, effectively, it compresses the target material. After that compression wave passes through, the target decompresses. It's called a rarefaction wave. And the rarefaction wave basically encounters the free surface and material starts to be ejected from the crater. Now the crater grows laterally and vertically in size depending on the total impact energy. The total size growth of the crater is limited only by the gravity of the moon. So for a given impact velocity on the moon, you're going to form a crater bigger than one that you would form on the Earth. And that is actually reflected in the styles of morphology that we see, which I'll show illustrations of throughout the different size ranges of craters. Eventually, gravity limits the size of the total final crater depending on the total impact velocity, and that's shown in this middle stage here. The target that was compressed and vaporized, some of it was vaporized, some of it was totally melted. That melt lines the wall of this feature called the transient cavity. The transient cavity is the biggest extent of the crater growth during the initial phase of the crater. It is not the final shape of the crater, and in fact it's much bigger than the final crater because the crater is now going to collapse, material is going to fall back into it, partially filling it again. And the ejecta, the material thrown out of the cavity, races across the surface being deposited as a blanket of debris. And in a nutshell, that's how craters form. Conceptually, it's actually quite simple. In detail, it's extremely complex. And the bigger the cratering event, the less we understand the mechanics of how they all form and evolve. Next slide. Now there's a dependence on the morphology of craters for on two bases. There's a dependence on size, and as we get from very small craters, we go from a simple bowl-shaped geometry to a very complex multi-ring geometry, and there's a dependence on age. Young fresh craters look very crisp. They have a lot of well-defined landforms. As they are eroded on the moon, they become much more indistinct. Now, how can something erode on the moon since you don't have an atmosphere or anything else? Well, effectively, they erode by other impacts. I can land a crater on top of a crater. That can partially bury it. I can continually rain micrometeorites on it. That will smooth rocky surfaces and erode down the surface. It's a very slow process. But effectively, the story of the moon is the continual accumulation of craters on top of craters. And so that progression actually is shown in this bottom illustration. The crater on the left, Copernicus, is nice and fresh, has a nice central peak, very crisp topography. The crater on the far right is Descartes, and that is almost completely buried by debris and eroded material. Now the graph at the top right shows the depth-diameter relationship of craters. And one thing you'll note is a very pronounced, this is a logarithmic plot, but there's a very pronounced break in the trend of craters. This is a plot for all fresh craters, and what you see is that there's a nice linear relationship between depth and diameter for craters up to around 15 to 20 kilometers. Then there's a different relationship, also a linear relationship, but a different slope. First of all, big craters are systematically shallower in proportion than small craters. Small craters are usually have a depth-diameter ratio of about 1 to 3. The bigger craters have a depth-diameter ratio much shallower than that, on the order of 1 to 10. So they're totally different slopes, and in fact, this diameter at which this transition occurs, we've seen it on all the planets now. We've seen it on Mercury, we've seen it on Mars, we've seen it on Venus and the Earth. It becomes much smaller as the gravity increases. There's a nice inverse scaling of gravity. The higher the gravity, the smaller the diameter at which this break in slope occurs. This one cross-section shows two different kinds of craters. The cross-section of a simple crater is a simple bowl-shaped crater. The line outlining, the black line outlining the crater, is what's called in the cratering literature the true crater. That is the actual crater that's been disrupted and excavated, and it roughly approximates the transient cavity. But that true crater is now filled with debris that's sloughed off from the walls and fallen back into the crater, and that's appropriately enough called fallback breccia, and that will fill the crater, basically shallowing this out to a shallower apparent depth than ordinarily you would have. With a complex crater shown on the bottom, you have a flat floor and you have steps, basically landslips along the rim that are a result of a high rim that was too weak to support it geologically, and it collapsed in a series of circular faults. And that, in fact, is what makes terracing in complex craters. Next slide. So let's look at craters, and we're going to go up in size now. We're going to start off with the simple ones and look at them as they get increasingly large. And simple craters are in a nice bowl shape. The depth-diameter ratio is about 1 to 3. This is North Ray at Apollo 16, which was a very fresh, nice, simple crater. It's about 30 kilometers. It's about a kilometer in size. It's 30 million years old. Now that sounds like a very long period of time. By lunar standards, that's very recent. And in fact, craters that are young tend to have rays, and the rays disappear with time as they're gardened into the regolith by micrometeorites. North Ray is called that because it is a rayed crater. And in fact, it has a very nice profile. These walls are quite steep. If you look at the surface photographs of John Young and Charlie Duke up at the rim of North Ray crater, it's very apparent they kept well away from the edge of the crater, because as they looked down into it, those slopes were actually greater than about 35 degrees. So it's a very steep wall, lots of blocks, and in fact they found one rock on the rim of this crater called House Rock. It was as big as a house. It was about 15 meters across. We've gone up in size here now, basically 4 times to Moisting Sea, and finally to Moltke at 6 kilometers. You see that fundamentally these all have the same morphology. They have a raised rim, they have a textured ejecta blanket, and they have a nice smooth bowl shape. And this morphology is quite common for fresh craters in this size range. Next slide. Now we're going to go up in size, and as you see, as we're increasing in crater diameter, the craters are getting increasingly more complex in terms of their landforms. This is what I call the simple to complex transition. These craters are not quite complex in that they don't have flat floors or central peaks, but they do have debris floors. They have floors where material is sloughed off the walls and accumulated in the bottom, so they're quasi-flat. And they also are starting to show evidence of significant landslip failure along the walls. One of the best examples is Triesnecker at 26 kilometers has a very nice big slump block. Clearly that crater was just at the diameter where it couldn't support the rim, and that rim collapsed inward toward the crater floor, forming this big slump mass. You might think, well, what's the significance of that? Well, it turns out that you can actually study the exposed rocks in this wall actually expose a nice clean section of the subsurface geology. Craters are our natural drill holes into the moon. And one of the things geologists always want to do is get down to bedrock, see through the overburden, and look at rocks that are deep below the surface. Craters allow us to do that. On the Earth, we look for canyons and we look for road cuts. On the moon, we look at craters. So what you see here is basically a progression in complexity as these craters get bigger and bigger, and we're starting to scallop the rim, we're starting to see incipient terracing, and occasionally we'll actually see little things that might be incipient central uplifts. They're not quite peaks yet, but they are starting to get floor roughening that looks like that. Next slide. Complex craters show very nice, clean morphology all over the moon. They have a raised rim, they have terraced walls, flat floor, and then a central uplift. And this pretty much holds throughout its range. There's some variation in the topography. King Crater, which is on the far side, has this lobster claw central peak, which is really kind of odd. Most central peaks tend to be just isolated mountains that stick up from the middle of the crater. This is actually, craters like this, like King, have called into question our model for how central uplifts form. And one way that's been postulated that they form is that you have this rebound phenomena, where as the terraces are forming and materials collapsing in toward the center of the crater, material from the front is actually being pushed up and actually comes up into a certain level and then is either frozen in place or collapses back down. This suggests that you actually had material come up and then collapse down, because the material that was uplifted then fell back on top of the floor that it was uplifted above. It's still debated in the cratering literature whether there's a push mechanism where the terracing pushes up the peak, or whether there's a pull mechanism where a rebound phenomenon actually pulls this material up before it then collapses into its final state. One thing that you do have that are particularly noticeable with very young complex craters, and Tycho is the classic example, is a beautiful ray pattern. The ray pattern of Tycho goes almost all over the entire front side of the moon and extends many thousands of kilometers away from the crater rim. Interestingly enough, we think we determined the age of Tycho, and we determined it because one of the rays goes all the way up north of the site and crosses the Apollo 17 landing site. And when that debris hit the Massif, South Massif at Apollo 17, it initiated a landslide that threw South Massif material out over the local basalt. By dating that light mantle, we know that light mantle occurred 109 million years ago. So therefore, we've actually dated the crater Tycho by going to the Apollo 17 landing site, because that ray, the arrival of that ray material, created a local event that could be dated by exposure age. Next slide. Now, as we get bigger, it seems like the craters are pretty much the same, but then you start to notice something different. You first see it at Langrenus, which is a classic example. It's a nice crater, about 130 kilometers across, a very nice central peak, but you notice you do see floor hummocks, little rough hummocks, that start to appear between the central peak and the wall. And then at Compton, you start to see that these floor hummocks that are actually appearing between the peak and the wall are starting to arrange themselves in a circular manner. So we're actually seeing here another transition. First transition was between bowl-shaped craters and complex craters. Now we're seeing a transition between craters and basins. So at Compton, which is 162 kilometers across, we have a peak, but we also have a peak ring. And finally, the most mature expression of that is the crater Schrödinger, which is near the south pole of the moon on the far side. 300 kilometers across, has a very nice ring of peaks. So this is what we call a two-ring basin. We've actually crossed the threshold from complex crater to basin. Now, that definition is arbitrary. We don't really have a perfect diameter at which we say that's no longer a crater, that's a basin. Typically, lunar geologists have used the diameter of 300 kilometers to distinguish between an impact crater and a basin. So Schrödinger at 320 kilometers across is a true ring basin. Next slide. And as we get bigger and bigger with these features, we start to get multiple rings. Not just two rings, an interior ring, but multiple interior rings. Korolev on the far side of the moon has a nice peak ring, but if you look very carefully, you will see small peaks that stick out between the center ring and the crater rim. And Korolev is about 440 kilometers in diameter. By the time we get to Orientali, which is about twice that at 920 kilometers, we have a nice, beautiful multi-ring bullseye structure. The main rim of the basin is right here. This is the Cordillera range. There are two Rook mountain ranges, the outer Rook, which is right here, and then the inner Rook in here. And then finally there's a little shelf-like ring inside. So there's actually 4 rings visible in this image. And the Orientali Basin is sort of the type example of a multi-ring basin. We're not exactly sure why multi-ring basins form or what they're really telling us. We do know that compositionally, the rings of multi-ring basins tend to be different than the composition of the material around it. So if the analogy with central peaks, where central peaks are brought of material that's deep in the moon, brought up close to the surface by impact, we think these rings are very similar to that these rings represent deep parts of the lunar crust that are brought up during the impact event. Finally, we get to the very biggest basins. Now, the biggest basin on the moon is South Pole Aitken. And what I've done here is just taken the topographic map and reproject it at the center of South Pole Aitken Basin and drawn on what I think the ring structure is. And this basin is 2,600 kilometers across, so it's more than twice as big as Orientali. In fact, it's almost as big as an entire lunar hemisphere. And the thought is if it was much bigger than this, it would have destroyed the moon. It's funny, ever since I've been in this business, and it's been 25 years, I've heard that it was originally applied to Imbrium. Imbrium is 1,100 kilometers across. And I was told by reliable experts that anything bigger than that would have shattered the moon. Well, here's one that's twice as big as that, and it didn't shatter the moon. Now they're saying, well, anything bigger than this would have shattered the moon. So you can take that for what it's worth. I note the significance of this feature. This is a documented impact basin. No one doubts its existence, and no one doubts its size. And you may have heard or read in the paper recently, there's talk about the Martian crustal dichotomy being caused by a giant impact early in its history. A lot of the evidence, the geologic evidence, for that basin on Mars is drawn from the lunar analogy. Because we know how to recognize very old, degraded impact features on the moon, we've learned how to recognize them on the other planets. So the fundamental dichotomy of Mars into the northern lowlands and the southern highlands was probably caused by an impact very similar to something like the South Pole Aitken Basin on the moon. Next slide. Now, basin geology fundamentally makes up the upper crust of the moon, because there's about 50 basins on the moon, greater than 300 kilometers in diameter. They span a range of ages, from the very oldest thing that you can see, like South Pole Aiken, up to the very youngest, like Orientali, that you can see. And basically these overlapping ejecta blankets thrown out by the basins. When a basin forms, and remember, Orientali is about the diameter of the state of Texas, is across. When a basin like that forms, it throws material out over many hundreds of kilometers of terrain. So you've got a huge ejecta blanket. So the highlands of the moon, which you see, all these craters, are basically stacks of this material on top of each other. The oldest basins are at the bottom and the youngest basins are at the top. Now you'd think you could just go at any place and read that record, recover it. The fact is, that's locally being churned up by craters that have formed after the basins. The bottom, this view shows the Orientali Basin and a geologic map. One thing to note about the geologic map, which is at the top right, is you see the distribution of ejecta, which is shown in blue, is not circular around the rim, but actually it's elongated. And we see that a lot with these basins. When you actually draw out the limits of their ejecta blankets, they're not perfectly equal distance around the rim in all directions. They tend to have a bilateral symmetry. And what we found is that this tends to reflect oblique impacts. If you have an impact that comes in at an oblique angle, it will send out ejecta in directions perpendicular to the flight path and form a nice, what we call a butterfly pattern. And Orientali shows this very nicely. The inferred direction of the Orientali projectile has to have been coming in from this direction, from the northeast, to basically make a butterfly pattern that's northwest, striking northwest-southeast. The map at the bottom is a map of the distribution of recent basins on the moon, taken from Don Wilhelm's book. And you can see effectively the entire surface of the moon is covered by ejecta blankets from one basin or another. The areas that are in white here don't show any basin ejecta blankets. It's not because they're not there. It's because these basins are so old that they've been beat up and churned up and mixed up, you can't really detect that anymore. You can't really detect those ejecta blankets. Next slide. Now, what does this have to do with landing on the moon and exploring the moon? Well, fundamentally, the Apollo missions all especially the Highland missions, landed in relation to one basin or another, in some cases deliberately and in some cases fortuitously. The first mission to the Highlands of the Moon, Apollo 14, landed in what's called the Fra Mauro Formation, which was basically the continuous ejecta of the Imbrium Basin, the biggest, youngest basin on the front side of the moon. And what this diagram shows is it shows Orientali as sort of a tight basin. These numbers up here reflect the position of a given Apollo site relative to the basin that I've listed on the left. So number 2, Fra Mauro Formation, is right here in the continuous ejecta of, in this case, the Imbrium Basin. And that's shown on the cross section up here at the top. Now Apollo 15 landed in the position number 3, which is right at the very topographic rim. So landing at the Apennine Mountains, that's the rim crest of the Imbrium Basin, Apollo 15 was right on the very edge of that crater. And the thought was that they would sample not only material thrown out of the basin during that impact, but also material that had been uplifted and exposed that predates the Imbrium Basin. So you're going to look both at pre-Imbrium Basin rocks and the ejecta from this large basin as well. Now Apollo 16 was a bit of a surprise, and we didn't understand this until after the mission. We thought Apollo 16 was going to go sample some highland volcanic rocks. But instead it returned impact products. The astronauts recognized this on the surface. They knew they were not sampling volcanic rocks. So the idea was, where did these impact rocks come from? Interestingly enough, Apollo 16 has an interesting position with respect to 2 basins. It is on the very distal edges, site number 1, of the Imbrium Basin. It's about 1,600 kilometers away from the Imbrium Basin. However, it is very close to the continuous deposits of the Nectaris Basin, which is an older basin, yet still one of the ones mapped on the front side. So it actually has the potential of having 2 different basin deposits in its sample collection. And to this day, we have not yet unraveled that relationship. We're not sure which samples are which. You'll have a special talk on the crust of the moon where these kinds of issues will be addressed. Finally, Apollo 17, the last Apollo mission, landed inside the basin on an inner ring. It landed in the Taurus Mountains, which is one of the inner rings of the Serenitatis Basin. The significance of that is that the inside of the basin is where we expect the melt sheet of the basin to reside. The melt covers the interior of the basin, including mantling the massifs that make up the ring. Now, basin melts are important because they are the product that you can date to recover, radiometrically date to recover the age of basins. And our understanding of the ages of these features, which I'll talk about in a second, largely comes from this kind of geological analysis. Very simple-minded and in fact may not even be correct, but it's our best guess at what's going on. Next slide. Well, in addition to circular craters, there's a whole bunch of bizarre landforms on the moon. I love to throw these up because this just goes to show that we don't fully understand everything that's going on the moon. Crater chains are common on the moon. Typically, they're secondary craters. As you form a crater, the material's thrown out of it, it hits the surface of the moon, and makes a crater by its impact. And that's called a secondary impact crater. Very common around fresh craters. This particular ring of craters here on the top left is the Spudis rill, which is actually a collection of secondaries from Copernicus. However, the Davy crater chain in the Central Highlands may or may not be a secondary. Now, we originally thought Davy might be a chain from Orientalis, a secondary chain, but that was before we saw Shoemaker-Levy hit Jupiter, where we saw a comet split gravitationally and actually form a chain of debris that went in and hit the planet sequentially. And it could well be, remember, the moon rotates a lot slower than Jupiter. Jupiter rotates once every 9 hours. The moon rotates once every 708 hours. So a rotating moon being hit by a tidally disrupted comet might form a crater chain just like this. And in fact, that is now how we think this crater chain formed. There are things called delta rim craters. That's a very odd name. It refers to the fact that if you look at the profile of the rim of this crater, it looks like a delta, a pyramid. It's steep on one side and steep on the other side. But what's really interesting about this crater is there's no discernible ejecta blanket here. You don't have textured ejecta like you find around orbital impact craters, and typically these craters are filled with volcanic materials, with lava. They may be volcanic craters. They may actually be calderas that people have always postulated, but the other possibility is they may have formed under unusual impact conditions. This particular crater is actually on the melt sheet of the Orientalis Basin, and it's possible that it formed while that melt sheet was still partially molten, in which case you're actually forming a crater in a partially solid, partially liquid target. It might leave a very different morphology. These craters do occur in several places around the moon. You find crater clusters all over the place. The highlands typically look like this, where you have bizarre craters that are on top of each other. They seem to interfinger. These are probably secondaries from large impact basins. The bigger the basin, the bigger the source crater, the larger the secondary. These Spudis craters from Copernicus are on the order of 4 to 5 kilometers across. But Imbrium, remember, is over 1,000 kilometers across. And this is your Imbrium secondaries. These things are about 25 to 30 kilometers in size. So they're very big secondaries. The significance of this is they're not going to form a melt sheet. If I hit a secondary, by definition, it's less than a lunar escape velocity. So it's going to hit at less than 2 kilometers per second. It doesn't have enough energy to make a lot of impact melt. In fact, what it does have is probably a cloud of debris that comes in and mixes up the surface. You also have bizarre volcanic craters. This is Aratus, Ca in Mare Serenitatis. Clearly it's not an impact crater, but it is a hole. It's probably a volcanic vent. You have craters that have been internally modified. Gassendi is in the middle. That floor has been uplifted, and you can tell by these cracks on the floor that actually indicate extensional stress on the crater floor. You have collapsed pits, and finally my personal favorite, elliptical craters. The bottom right shows the Messier A and B pair, which actually have a beautiful ray pattern. Partly it's 2 cat whiskers that go off in this direction, and then a butterfly pattern that goes off perpendicular to the flight path. We estimate that this thing was formed by either 1 or 2 impactors that came in at less than 5 degree incidence. So it's a very grazing impact. Next slide. The Maria cover about 16% of the moon total. It's concentrated on the far side, although we do have some on the front. They're basically flood lavas. This one image here shows a nice flow lobe. Interestingly enough, studies of the rocks returned back suggest that lunar lavas, when they're liquid, are very low viscosity. And if you want to know how low, we think it's probably about the viscosity of motor oil at room temperature. But they're erupted at rates of tens to hundreds of cubic meters per second. Extremely voluminous, extremely fluid material that spreads out on the moon. And these Imbrium flows actually traveled over 200 kilometers on a slope that averages less than 3 degrees. So it's a very shallow slope, but they travel a very, very long way because they're very fluid and they're very voluminous. They're very thin. Mare typically are less than 100 meters thick, except in the very center of the basins. And these two maps, the one on the top shows age of Maria, the one on the bottom shows the composition of the Maria. What this shows is the Maria is not a single big massive unit, but a series of very small flows and placed over quite a long period of time, at least 100 million years of time. It seems like there's a lot of lava, a lot of different flows, but in fact, if you think about it, if there were 100 flows and placed over 100 million years, you might never see a flow in your lifetime. The flow might only occur on average of one per million years. So it's a very, very low rate of volcanism. Now you can compare that to either Mars or Venus, where in Venus in particular, there's probably flows now that are forming on the planet because we think it's volcanically active. So on Earth and on Venus, big planets that are active, you have a lot of flows, but on the moon it's actually quite a cool object. Next slide. Two basic types of volcanism: flood eruptions, which is the most common, that basically makes the large flows that we saw in the Maria that I showed earlier. And what happens here is you have a fissure and the magma comes up to the surface and is erupted in big effusive volumes. It's literally a flood of lava, and that's why they're called flood lavas. We have these on the Earth. We have them in the Columbia River Plateau, which are flood basalts. Also in the Deccan Plateau in India, those are all flood basalts as well. So it's a common style of volcanism on the planets, and we really understood it first by looking at the lunar Maria, and then we had to understand how flood basalt volcanism worked on the Earth. Occasionally you'll find central vent volcanoes. These little domes here are little small shields. They're about 4 to 5 kilometers across, but they're beautiful little shield volcanoes, very similar to what you see on Earth in places like the Snake River Plain, where you have a lot of little tiny shields, little eruptive centers that form small volcanic constructs. Sinuous rills are lava channels, very similar to river channels except carved by flowing lava, not by flowing water. Now the other style of volcanism on the moon is not lava, but rather pyroclastic ash. And that typically takes two forms: small localized deposits. This particular dark halo crater you see occurs along a fissure. It's an elongate shape and has a dark halo around it. And that's a dark halo crater on the floor of Alphonsus on the front side of the moon. You also have regional deposits around Rima Bode. This long fissure vent here with this kidney-shaped crater actually erupted a huge blanket of dark material that covers many hundreds of square kilometers all over this part of the moon. Next slide. Okay, so that's sort of physiography in a nutshell. We've covered the impacts of the moon, all the size ranges from the very smallest to the very biggest. We've looked at the Maria and how they form and what landforms they form. I want to spend the last few minutes on geology, but specifically I want to talk about stratigraphy because no one else is going to talk about this. You're going to get talks about some of this other stuff. But geology is the science that describes the history and processes of solid rocky bodies. And I want to give you a brief feeling for what these other subjects are, so when people talk about them, you'll know what they are. Next slide. Geochemistry, as the name implies, studies the chemistry of planetary materials. We're interested in the elemental composition of them. And in the case of the moon's depleted in volatile light elements. That means it's depleted, it has less of them than Earth and meteorite material does. But it's enriched in refractory element. A refractory element is one that has a very high boiling point. So elements that have high boiling points are enriched, elements that have low boiling points are depleted in the moon. It's also depleted in iron relative to the bulk Earth. The density of the bulk Earth is 5.5 grams per cubic centimeter. The moon's 3.3. So what's the difference? The most cosmically abundant element that's dense is iron, and it's depleted in the moon. And what's the reason? Because the moon doesn't have a big iron core. The Earth has a huge iron core. The iron core is at least 50% of the volume of the Earth. The moon has a very tiny iron core that's probably less than 1% of the mass of the moon. It's also depleted in iron-loving elements like nickel and cobalt and iridium. And that's an interesting clue. It's an important clue as to where the origin, how the moon formed. And we're not quite sure what it means, but the bulk composition of the moon is very similar to the mantle of the Earth. If you look at the picture of the Earth, you got the crust, the mantle, and the core. If you took the mantle of the Earth and held it in your hand, that would be a good rough estimate of the bulk composition of the moon. Next slide. Now, mineralogy and petrology. This is very simple. They love using jargon terms. Mineralogists and petrologists have there's 30,000 minerals on the Earth, and you can describe any combination of them with a rock name. But fundamentally, mineralogy is the study of how elements are in coordination with each other. So, rock-forming minerals are crystalline structures. The elements arrange themselves with respect to each other, and that's mineralogy. And with the thousands and thousands of minerals on the Earth, you'll be pleased to hear that what I've listed here on this slide are virtually the entire minerals of the moon. This basically is lunar mineralogy in a nutshell, and it consists largely of 5 groups. Plagioclase, which is the light-colored aluminum calcium-rich stuff. Pyroxene, which is the dark phase. Olivine, which is a greenish magnesium-rich phase. And the oxides, which are largely on the moon an iron-titanium oxide called ilmenite. If you understood the mineralogy of these 3 mineral groups, you effectively understand the mineralogy of the moon. Petrology is just the arrangement of minerals. So mineralogy is the arrangement of elements. Petrology is what minerals they are and what proportions they are. Basically, the maria are basalt, which are rich in pyroxenes and plagioclase and ilmenite. The highlands are rich in almost completely plagioclase with minor mafic minerals. So in a nutshell, that's what mineralogy and petrology is on the moon. Next slide. Needless to say, there's a lot more detail, which you'll get in a subsequent talk. But I've given you the guts of it. Structural geology basically refers to the deformation of the solid moon and study of faults, basically. So when you put stress on the moon, then the crust responds with deformation and in some cases failure. Compression occurs. When compression occurs, you form ridges, and that's what the wrinkle ridges of the maria are. In detail, they're very complicated. They have a lot of overlapping morphologic elements. They're very hard to understand. But think of it simply as a rug in a room, and you kick it up and you press it together. The stuff will come up in folds, and that's what a wrinkle ridge is. You're basically compressing the maria surface and you're folding it into this kind of a form. Now, extension is where you actually pull the crust apart. And that occurs on the moon in the form of things like graben, which in the case are two faults that parallel each other and you have a block that's down drop between them. This is a particularly beautiful example of one that crosses both Mare and highland boundaries, a down drop block. It's called a graben. It's a German term. Or you can have a single fault where you just have a high side and a low side, and that's this normal fault here in Mare Humorum. Strike slip, which is like the San Andreas in California, we do not see those kinds of faults on the moon. At least if they do occur, we don't know where they are. Interestingly enough, for the circular maria, you see extension on the edges and you see compression in the middle. And the reason for that is as you have a thick lens of Mare basalt lava, which is a fairly dense rock, it sags, creating extension on the margins and compression in the middle. And in a nutshell, that's the structural geology of the moon. It really is literally not any more complicated than that. Next slide. Geophysics is a study of the whole body of the moon as a whole body. And you do that in a lot of different ways. You do it by seismology, you study the heat flow, you study the magnetism. But what we've learned from geophysics is that basically there's a crust that's anywhere from about 35 to 50 kilometers thick on the near side and 80 to well over 100 kilometers thick on the far side. It may be layered. It may be that the upper part of the crust is slightly less iron-rich than the lower part of the crust, but we don't know that for certain. The mantle, which extends from the base of the crust down to about 1,300 kilometers, remember the moon's radius is 1738, is basically the source of Mare basalts. The mantle is the rock which, if you melt it and erupt it, you have a Mare basalt. So we can actually take the Mare basalt, we know what its composition is, and we can work backward to what the mantle is like. Because we know if we take a certain mineral assemblage and melt it, partially melt it, to certain degrees, we will get a basalt composition. What this tells us is the mantle is composed primarily of two minerals, olivine and pyroxene. And that's just like the Earth. We also have the example on the Earth where lavas have ripped up part of the mantle coming up to the surface. These are called xenoliths. And we've looked for xenoliths on the moon, haven't really found any. But we suspect the lunar mantle is very similar to the terrestrial mantle because basalts are just like the ones we see on the Earth. And finally, there's the core that I mentioned. It's very tiny. This is a cross-section of the moon. The core is in the center. Basically, it can't be much bigger than about 400 kilometers in radius. And that means that it's less than 1% of the lunar mass. Next slide. All right, now I want to talk about stratigraphy, which in fact is, this is how we understand geological history. And the stuff I talked about earlier about craters. We're actually going to see how you can use photographs to establish a chronology, because that's largely how the moon has been mapped, from photographs. Not in terrestrial geology, I go out in the field, I pick an area, I walk around it, I take an aerial photograph, I draw out contacts, I sample each one. That's how you map on the Earth. We haven't had that luxury on the moon. How do we understand what the history is? Well, basically we use photographs to reconstruct this. Stratigraphy is simply the study of layered rocks. It comes from the strata, which basically means layers in Latin. And you determine relative age on the moon by overlap and by crater density and degradation state. If I have two craters and I have one ejecta blanket on the other, I know this crater is younger than this crater. Right? If I have two lava flows and this one has a lot of impact craters and this one has less, I know that this one is older because it has more craters. It's been exposed to space longer. If I see one crater and it's fresh and crisp and has rays and a nice ejecta blanket, and then I have another one that you can barely see, I know this crater is younger because it's based on its degradational state. So those three things all can be determined from a photograph, and that in fact is how we map the moon geologically. It's been keyed to events on the front side of the moon and basically divided into these periods. It's not important that you remember them or their ages, but I do note that it covers the span of lunar history. Copernican is the youngest period on the moon, and that's the period where you have the least amount of activity. Most of the activity on the moon occurs back in the pre-Nectarian, the Nectarian, and the Imbrian. So you have both rock and time units. A series of rock units are called formations, and a system is basically a collection of formations that formed around the same period of time. This chart from the right is taken from an older book. You'll see it has different ages than I've listed here. The ones that I've listed are our current best guess of what those ages are. These were earlier estimates, and they may or may not be accurate. Next slide. All right, so how do you map something geologically from a photograph? Well, this is the classic area to show you. This is the Apennine Mountains. By the way, the Apollo 15 site is right there. One thing to note, you've got two craters here. This is Aristillus up here, and this is Archimedes. What's the difference between the two? Well, Archimedes is flooded with lava, but Aristillus is on top of the lava. So which one is older? Anybody? Archimedes is older because it clearly predates the lava, because it was there and then it was flooded by the lava. But Archimedes is on top of whatever this is, which is the floor of this basin. The Imbrian Basin rim comes through right like this. All right. So this ejecta material from this is actually older than the Maria, because the Maria fills the basin. So what we've done is we've actually classified a sequence here based on photographs, and that's shown in this geologic map here. Yellows and greens are young, and browns and dark blues are older. And basically this simple way of mapping sequence, of seeing pre-basin craters, pre-Mare craters, post-Mare craters, is how we map the moon geologically. Next slide. The image at the top is a global map of the moon, front and back. Front's on the left, back is on the right. And again, you see that in particular the western hemisphere is dominated by this Orientale basin, which I showed earlier on a basin-centered map. Most of the Mare is concentrated on the front, although we do find some on the back. And the highlands are very complicated, a lot of different colors. What that reflects is the endless sequence of crater upon crater upon crater that have built up the highlands. So it's a very pounded, beat-up surface, and yet we can recognize structure and stratigraphy within it. I also show the South Pole Lake and Basin again. I've taken the geological map and reprojected it so it's at the center of the basin. And you see it's not really evident by the pattern of geological units, because basically all we've had are craters and mare that have formed on top of the basin. It doesn't really tell us much about SPA itself. You do see SPA's influence in a topographic signature and in compositional signatures. The principal compositional anomaly on the far side of the moon is associated with this basin floor. Next slide. So from this mapping, we've actually derived the geological history of the moon. And now I've also incorporated what we found from the samples. But fundamentally, you accreted the moon and you melted it globally. That's inferred from the samples. The heavy bombardment and the basins comes from the geological mapping, because we've seen a very long, protracted history. Mare volcanism comes from both the mapping and the samples, which occurred next. And finally, the impact and regolith growth. Now, this diagram I've shown here at the bottom is a plot that I made for the new solar system book, where we talked about the moon. And in this diagram, the present is at the very top, 0 years before present, and the beginning of the moon is down at the bottom. And the width of these envelopes, whether it's bombardment rate or magmatism or volcanism, is proportional to the rate of activity. And what this shows is almost all the activity on the moon occurred very early in its history, and that tapered off very rapidly as the moon, as we approach the present. Next slide. Now, you may say, well, what relevance is this? It turns out that the moon is actually quite significant because it accompanies the Earth in its journey around the sun. So if we can read and recover the impact flux on the moon and understand it in a detailed manner, we can infer what the flux was on the Earth. What we found by studying lunar flux is there is a very pronounced peak in ages of impact rocks around 4 billion years ago on the moon. This is called the cataclysm. In fact, the idea is that all the basins formed in a very short period of time. Now, the reason that's significant to the Earth is this time, 3.9, 3.8 billion years ago, is about the time that life emerged on the Earth. Now, the question is, did life emerge because the bombardment ceased, or did the bombardment actually act as a driver of evolution, actually spark the origin of life? And the reason that that's not a crazy idea is because we've seen in subsequent lunar history, large body impacts that occur in Earth history open up ecological niches that drive evolution, create very fast evolutionary growth rates. So understanding the early impact history of the moon will help inform us about what the conditions on the Earth were as well. Next slide. These are a series of paintings that Don Davis prepared, kind of showing how the moon's surface has changed over the years. And the oldest moon he's drawn up here at the top left, that's the Precambrian moon, as the moon as it appeared about 4 billion years ago. These next four drawings show the Imbrium Basin impact. Basically, he has a 100-kilometer object hitting the moon, forming a giant crater that grows. The rings come up possibly through some kind of an oscillatory mechanism, and the eject is thrown out and basically deposited across the entire front side of the moon. This is the final configuration of the basin about 3.85 billion years ago when the basin formed. Now, immediately after that, you started erupting lavas that started filling the surface, first in the center, and then finally more extensively inside and outside the basin. You formed craters like Eratosthenes and very young, the lava flows that I showed earlier, the nice flow lobes, or the late Imbrium flows here, and that was done at about 3 billion years ago. And finally, the last stage here over at the right is Copernicus formed about 1 billion years ago. You see there's not much difference between this, which is the present moon, and this, which is the moon about 3 billion years ago. Next slide. And that's really driven home in these three pictures, which kind of show us the moon as it appeared at three different stages in its history, including the present moon. The Imbrian moon has occurred just after the Imbrian Basin formed, and then this is the Eratosthenian moon when most of the Maria had already been erupted. And you see there's not much difference between the middle one and the bottom one, except for the presence of rayed craters like Copernicus and Tycho. Next slide. You can also do this geologically. I showed geologic maps of the moon, but as you take off younger units, you can actually see the underlying geologic structure. So here's a geologic map of the moon at 4 different times in its history. The bottom right is the present moon. We strip off the youngest craters and we see the Eratosthenian moon. We strip off the lava and we see the Imbrian moon. And finally, before the Imbrian Basin, we see the Precambrian moon. So this is a very powerful technique. Just by using the photographs and determining what the relative sequence of events are and using fresh features as our guide to what these old features might have looked like when they were fresh, we can actually reconstruct the moon at different times in its history. Next slide. I want to close a little bit by talking about cartography. Basically, there's a lot of maps available of the moon. I think maps are very important because maps give you a feel for both process and scale. You get an idea for what kind of landforms you're going to encounter, what kind of processes you're going to be studying, and also how big they are. How far are you going to have to travel in order to do this? The first step typically involves making a photomosaic. You might have photographs taken at different geometries with different lighting conditions. You try to reproject them so that they're all consistent viewing geometry, and then you just cut them out and mosaic them together. This particular map of the northern part of Orientali was done during Apollo, and it was all hand-laid. We do this digitally now. We take the images, digitize them, and the computer will reproject them. But one very powerful technique has been to take photographs and actually do what they call airbrush drawing. You take an airbrush and actually literally draw the terrain. And the idea here is you can take images that taken at a variety of geometry and lighting conditions and make them appear uniform so that the surface looks as though it was all illuminated under one ideal condition. And the final product is what you see down here at the bottom, which is a shaded relief map of the central highlands of the moon. Now, this is an artistic drawing. It's not a photograph, but at the same time, it makes a very good base map for plotting information because you know where the features are and you also know what they look like under uniform lighting conditions. Next slide. There are a variety of different maps of the moon. And I start off with my personal favorite. If you have any interest at all in the moon, I strongly urge you to get the National Geographic Society map. There are 2 versions of this map available. One was published in '69 in association with the Apollo 11 mission. Don't get that one. It doesn't have any of the far side craters. They published a second edition in 1976 that has all the far side craters on it. It's $20. It's the best $20 you'll ever spend. But if you're really cheap and you don't want to spend that, you can go to the USGS website and download their version of it, which also has the Clementine topography on top of it. And those are free. You can download those and print them out yourself. There's a variety of different topographic shaded relief maps and geologic maps. This covers the entire front side of the moon. There are special large-scale maps plotted on orbiter photographs that actually have the Apollo landing sites and including the big global sites as well. I include down here at the bottom, there's a link where you can go virtually all maps of the moon are available at the LPI website, and you can download them for absolutely nothing. If you have a big format printer, you can print them out at full scale. If not, they look great at page scale as well. Next slide. So I've included at the end some references. The good thing about the first 4 entries to this reference list here is that you can download them all for free at the links I provided. They're available as PDFs, and they're all sources of very good information, very well put, very well written, I think, and accessible to anybody. Next slide. All right, I want to close with a look ahead. 2 weeks we'll hear from Jeff Plesha on the lunar regolith and dust. And you've got the agenda for the rest of it. Next slide. I've posted this presentation. It's already at my website. If you want to go to this and go to the Moon 101 link, and you'll see all these presentations listed. Thank you much, and I'll take any questions you have. That's good. Yes, Dean.
This is sort of a leading question because I wanted to emphasize something, and you're the lecturer. But the significance of recognizing impact as a geologic process from early in the century to where we are now.
Right. Yeah, I'm often asked by a lot of media people ask me, what's the single most important scientific result we got from Apollo? And I always say that appreciation for impact was the most important one, because we had to understand the lunar samples, we undertook a crash program in the 50s and 60s and the 70s to understand the physical and chemical effects of large body impact, which are really quite profound. They have very distinctive markers, both chemically and physically, that they leave in geologic materials. Because of our need to understand what the Apollo rocks were telling us, we developed an entire database of information on that process, that physical process. And that actually led to the recognition of the KT boundary impact. Because what we found in there was, 1, elevated amounts of iridium, which is rare in the Earth's crust, but is very common in meteorites. Secondly, we found grains of quartz that had been shocked, where you have a shock wave pass through it. Shock metamorphism is unique in geological studies. Most metamorphism is high pressure, high temperature for very long periods of time. Shock metamorphism is megabars for microseconds. Basically, you have very, very high pressures for very short periods of time, and it creates a unique geological signature. We found the shock quartz and the iridium in the KT boundary, so we're able to say that whatever caused the mass extinction at the end of the Cretaceous, there was a giant impact too. And when we look in the record, we see other mass extinctions, we also find evidence for impact. So the idea that impact may actually drive mass extinctions and therefore drive the evolution of life came about because we went to the moon. Now you can always say, well, we would have figured this out eventually anyway, and you may be right. But my point is, because we went to the moon, because we had this knowledge, because we were forced to understand the Apollo samples, we got a completely different picture of how life evolves on the Earth. I think it's a pretty profound result, and I think we got that almost entirely thanks to the Apollo program. Thanks for setting that up. Just keep lobbing me those softballs. Any other questions, comments, complaints?
Question from the loop.
Yes, sir.
You keep, for the ages of craters, you keep using the term GA and MA.
I'm sorry. Yeah, GA is giga-annum. It means billion years, 10 to the 9th years. MA is mega-annum. That's 10 to the 6 years.
Thank you. That's
geo speak for billion years and million years. We do that, actually, it's not totally silly. Billion in traditional English usage is a million, is 10 to the 12th. And it's the American usage of billion that means 10 to the 9th, 1,000 million. So that's why we do that. Giga is unambiguous, 10 to the 9th. No other questions? Thank you all for coming. See you in 2 weeks.